Alright, welcome to the second part of this tutorial. We finished last part just producing like an initial matrix, something like very basic that took a while because I was explaining a lot of things. How to generate this list of lists with random values. So basically it's a matrix. Think about it as just like a X and Y two-dimensional matrix with columns and rows, and basically we are just creating like at each cell of this matrix, right, or each position of this matrix, a random value. That is my initial condition basically for this reaction diffusion simulation. So let me just go back to the original state of the code. Basically for now you should have something like this. I will put the code, of course, the source code for this, so you don't have to worry about that. So we need to create a couple of more things. In our functions we will use also a function that needs to copy the matrix, to generate at each iteration the calculations that we're doing. So let's call this with a source, and we will say that we'll create an empty list. That's what I like about Python, that you don't have to do like weird stuff. Sometimes it's like very efficient in the way that you code stuff. When you create a definition, a function, you just need to indent one time. So we will iterate for I in range. Again, we will use height. Oh, sorry, no. Range, we will use the length of the source matrix. So here, basically, we're saying that iterate, do a loop until you reach as many times as elements you have in this source list. And here what we're going to do, we will create another list, a placeholder for j in range, len, source, but this time we will iterate through the basically the number of elements that we have in one of the lists, because we're iterating like through all the lists but also through all the elements inside that list. So we can do something like this, and here we will do list.append, and here we will do I and j. Source, if I'm correct, yes, this is the way, if I remember, we can do it. And then the result, that's the way I named the list, the result at append list. So I will explain what to do here, but first we need to say also like return res. Basically, this is just like a help function that will take a list, this bidimensional list, this matrix, and it will create a new list, and it will copy it by iterating through all the lists, but also it will create a new temporary list that will basically copy each element of each list, and then it will added to this resolution. So basically in the end we're just like iterating and copying all the elements. This is kind of like dumb in terms of because you can do it with less code in Python. Trust me that I had some problems, so this is the way that we're just going to do it. If we're using NumPy, you just use like one instruction and it will do all of this. So we will see that in the bonus tutorial of this Python stuff. When we use NumPy, probably we'll modify this code, or I will show you how to do the same thing we did here with just like a couple of lines. So don't worry about that. It's a little bit like stupid. I know what I'm doing here, but trust me, it will work. And also we need to define another help function that is a null matrix. And for this, basically we will copy this. We will do the same thing here, but here in this case we will do height. Sorry, height. We'll create a list, and this will be width. And here we will just create actually not a null matrix, a matrix full of zeros. We're doing basically, instead of copying here, we're just creating a matrix that it just has zeros. If we were using NumPy, we would just do something like np that's zeros, and we will just do like the shape and do like, I don't know, 50, 50. I think that's the way you do it, if I remember correctly. And this will do exactly what we're doing here. So this is why it's important to use NumPy, and it will do it faster. You don't have a way to use it by default. NumPy inside Rhino. I hope someday, on Grasshopper, sorry, I hope someday we can, but for now we don't. But now that we have these functions, actually those are okay. We would just like fold this, hide this. Also like the init matrix, we don't need it. Have it open. We will define, actually this is the meat of our code. So basically this is the main part. This is the solver. A solver, as the name explains it, basically it solves something. Through iterations, through many iterations, it will start taking these equations, this reaction diffusion equations, and it will give you a matrix with values that will give you basically like the concentrations of component A versus component B. And this is why we need, for example, these helper functions, or basically this this is copy a matrix. Perfect. And here we will say create a matrix full of zeros. Perfect. So now the solver. We will call it def solve, and the parameters to use this will be the following. We need the concentration A, concentration B, and the number of iterations. Right. Again, the result of what we're doing, the quality of what we're doing, or even like the aspect, the aesthetics of what we're doing, it will sometimes increase or will be like better if we have more iterations. But that will take like a lot of time. So for now we will just like concentrate on writing this, and I will show you why. So we will start with the first matrix. We'll call it like AN, and we will call null matrix. I know that null matrix is not the best name because it's not a null matrix because it's not full of null or non elements, but that's okay. Bn is equal to null matrix so when we execute this will create a matrix full of zeros and a matrix full of zeros, because that's what this will return. And here global A0, and here's like global B0, and this is the main part, and this is basically, these are equations that you can find anywhere, even like in Wikipedia, as I was showing before. These equations here we will use if you, for example, go to this page, this website, and CSAIL, Computer Science and Artificial Intelligence Lab, we have this nice explanation about what is the Gray-Scott reaction diffusion, and you will find like super interesting stuff. So for example, here if you go to the Gray-Scott demo, you will find like an interactive demo that you can execute. You can find concentrations, and so on and so forth. Basically the equations are this, and the thing that you need to, these are differential equations, partial differential equations that you need to integrate. That's the opposite of like derivatives. If you remember like high school algebra, linear algebra, you're taking linear algebra. If you don't remember what are those, you can go to Khan Academy. Khan Academy, they have like really nice tutorials on linear algebra, derivatives. So for example, you see like integrals. It will basically give you like interesting videos. Actually, that saved me a lot last semester when I took this robotics class at CSAIL, because the last time I had proper linear algebra or calculus classes, it was in 2003 when I was in undergrad. So yeah, a long time ago. I was in the middle of my undergrad education in architecture school. So because I had to take classes last semester that were like really intensive on the algebra side, or linear algebra side. Yeah, like Khan Academy was really good to understand many of the concepts. So in order to do that, we need to use this function to integrate. So we will use the Euler method to solve the differential equations. You can find what is the Euler method. So basically it's a way to solving like first order equations and blah 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 with like initial values and things like that. So I mean, I won't extend in the explanation of what this is. Basically we need to, of course, use for loops to iterate through the values, to read the values of our matrices and stuff like that. So this is why, for example, using anemone or like hoop snake or stuff like that will not do the job, and sometimes you just need to use coding. So we will do for n in range the iterations. Remember that we have, actually we called it steps, but we will call it here like iterations. We will deal with that later. Now we will say like for I in range, we can use like the height. It could be the width. Basically we just need the number. We can actually set this as one parameter, just like n divisions or whatever, or grid size. And basically here, because we are calculating a matrix, we will have a boundary condition. So I will explain this with this diagram. And in this diagram, you can see that we will have, if we are calculating with a square, we will have this boundary edge condition. Because the reaction diffusion, basically what it's doing is taking into consideration the neighbors of each individual value. If you have one value, let's say in a matrix, in a grid, the value 5, x5, y5, you need to calculate the value in the next iteration according to the neighbors. But at the edge, you don't have those neighbors. So basically you need to treat this matrix, or the surface in this case, as a torus by wrapping the edges. So basically you will establish that if you don't have a neighbor, just like do a special case, to define the special cases. So we can say that I plus 1 equals to I plus 1. We can say that I minus 1 equals to I minus 1. And we can say that if we can start like saying this condition, I equals 0. Remember that to do like a comparison to check if something is equal to something, you use like the double equal sign. If you just use 1, you're assigning a value, so that will throw an error. Just a small reminder. We will say that if I equals to 0, we will say that I minus equal to height minus 1, of course. Oh, damn it, sorry about that. This keyboard is driving me crazy. I need my mechanical keyboard. Then we can say that another special case, if I equals height minus 1. I'm missing a parenthesis here. Minus 1. We will say that I plus 1 is equal to 0. And with that, we are fine. Yeah, those are our boundary conditions. So now, in this case, so now we will do for j in range width. And here we will say that j plus 1, this is another, in the other direction, it will be j plus 1, j minus 1 is j minus 1. And again, we check the other condition in the other direction. We said if j equals to 0, we can say that j minus 1 equals to width minus 1. Is that correct? Yes. Well, we will check if we get an error. We can fix it. Is width minus 1. Yes. The other one will be then if j equals width minus 1, j plus 1 is equal to 0. Yeah, just like we did with the I, with the height, we're doing it with the width. And now that we established this, we can start calculating how our components, the substance A versus substance B, they start to interacting and basically generating this reaction. So calculate component A. We will say that the A will be equal to component A, and this is a little bit of a nightmare. So I will do it with 1, and then it's like very repetitive, so I will skip that part and you can copy this or check the code. Basically this is the equation that we will write, if I remember correctly. It's like A0 I plus 1 is it like this? Yes, J, because we're iterating over a matrix. So 2.0 times A0, and we will say like I minus 1 J So you know that here we're just iterating, assigning the values through those matrices. This is the I and the J in the iteration, so this is why it's being written like this. Minus J plus A0, and we will do I, and this will be how was it? J plus 1. I should have my notes with me so I don't make any mistake. One thing also, like, it's important in, sorry, I put 20 here, to specify that this is 2.0. If you just say 2, this will create an error because 2 is an integer. So in Python, even though you're not explicitly declaring that something is an integer, string, or in this case just numbers, like this is an integer, this is a floating number, like a decimal number, the way you do it is just by specifying this. If you write this 2, basically you're mixing things, and you will do like, sometimes you will get an error, but sometimes you will get also like the wrong values, like rounded numbers. If you have an integer, probably this will give you an integer number. So imagine if you're calculating values between 0 and 1, like normalized values, you will have zeros if your number is calculated at minus, that means like lower than 0.5, or it will be 1 if it's bigger. So you will get like either 0 or 1, and that is not what we're looking for. So please remember that you need to have this 0 here. Okay, so this is minus 2.0 times A0, and this is I, this is J, plus A0, and this is I, and this is J minus 1. And close the parentheses. So this is the first calculation that we're doing, like so actually it's not that hard. Let's finish the this is the reaction of A, and this is A0. Let's finish the first component A, and then we will do another component. If you listen to this awful noise in the background, it's because workers are trimming the branches of the trees, so I apologize for that. If you can listen to that, if not, that's okay. So this is the reaction. So we will say that A0 is equal to I, this is J, times B0 I J minus A0 ij minus 12.0. That's the way the formula is. And an, basically the matrix that we are using to calculate everything, an, the value at the cell of that matrix will be and ij equals to a0 I know it's not the most fun part to do this, but when you see the results you're gonna see that it was worth it. So 0.01 times, here we do the reaction A plus the IA. Good. I think that we have a good initial thing. So now this is for calculating the component A, and we will say that this is an if statement. An ij is less than 0. It could be because we don't want to get like values that are less than 0. We'll say that an ij equals to 0.0. That's good. If I remember correctly, the component B is calculated the same way, so I think we can copy this. Control C, Control B. If you copy that way, you maintain the indentation, so our code looks pretty good. So we will change this Bn. This is B0. This is the reaction B, B, E. This one, reaction B, stays, I think, the same. I'm cheating a little bit here, but that's okay. So to calculate B, you do, of course, B0. I plus 1, minus 2, I'm just checking the values. B0, I minus 1, B, J, this is B, this is B, of course. Then the reaction B, this is different. The reaction B actually is, we will write it from scratch. This is 16.0 minus A0 ij times B0 ij, and this value Bn is equal to B 0.01. Really, this is correct, and we will of course add the same condition here. Indent this the correct way. We will say that if we get a negative value, we will just like say that that value is just equal to 0. And because we're calculating this over and over, we need to, you see, I'm maintaining this line here, maintaining the indentation. We will need to say that A0 equal to copy matrix, because we need to basically copy the matrix in order to calculate the next iteration. So the matrix that we are going to copy is An and B0. So when this enters the loop again, basically it will do it with the next value. Copy matrix, and this is bn. An and bn, it makes reference to the each step and steps that we're using for this. This should be okay. Let's test this. We have, of course, here one mistake, unexpected token. This is line 52. Let's see. Line 52. For I in range. Of course, I didn't use that. Let's see. Line 68. And we have unexpected token in line 86. You need to basically invest a little bit of time to get rid of all these mistakes or coding errors. So we will make this bigger. Line 86. So let's see what we did wrong here. J plus 1. Oh yes, here was my mistake. And of course, because we copied everything, if you don't do this, you're not a real YouTuber, right? To debug your code online. So yes, let me fix the indentation here, because basically you want to do this each time you finish this, at each step. So basically you're copying the matrix in each step of this iteration, not when you're going through the steps. So now we have like the main part of the code implemented. What we need to do now is what we can do, we can just try to see if this works. So we can specify our main call. We can say that the width equal to how did we call our parameters? We can say like u res height b res. We'll explain the name of this. Seed equals 1, a0 equals an empty list, b0 equals an empty list, and we can do like init matrix. We'll call the functions seed. We will solve. And for this we will do con A, con B, and calculations. And I think with that we are okay to do something. Let's see if we get like any errors. Probably we'll need to solve. Oh, probably I wrote something because I was looking for I-99. Oh yes, this is, I was looking for a Google Colab where I had my notes actually. Outer indentation, line 100. Yeah, we need one more space here. You see these are indentation errors. U res is not defined. Actually we called this we don't need this right now actually, so it's okay. Init matrix is not defined because it's the I with the lowercase. Con A is not defined. Concentration A and concentration B. Right, we didn't define those. So let's do that now, because we define which type of concentration we're going to use in the end, but we need actually those values. So we need to say con A, and this is a float, and this is con B, and this is also a float. Let's move this guys here, and we can say that this is, I don't know, 20, .0. If we do more values than this, probably it will not work. So let's say start with like known values like 0.5 for example, and 0.5, enter, and let's do the 16 here. Let's see if this runs. Calculations. Oh, we did steps, so we will say that calc equals steps. Oh, calc. Height is not defined, line 52. Sorry about this. Typos. Int has no len. Okay, so after you debugged all your mistakes, so for example I had like stupid like parentheses or stuff like that, check your code. After you do that, you can basically call the main functions to solve this. So right now the solve is not returning anything. I will do two things. We will say that A equals A0 and B equals B0. This will of course give me an error that we don't have a B here, so we will add it. This is giving me one error, yeah, indentation of course, always indentation, yes, of course. So let's see. Actually, we should do this here. Otherwise, we will get like each time a new thing. So if you press test, this should calculate what we're doing. We don't have any errors, so I think we're good to go with our final part, that we will the last function that we will create in the next and final part of this video. Right now it's not giving any error, so it is doing calculations. So if we say, actually we are going to delete this because there's no point. We'll say like print A0, print B0. This will be like a large print, so probably I will regret. Yes, it's giving me the warning that we're getting too many values and it will be impossible to print them, or we will use a lot of memory. So you can see here that everything is working. We're getting feedback. Actually, it's going crazy in Grasshopper panic because I'm trying to print a lot of values. So we will leave this video before my computer crashes and I lose this video until here, and let's wait for part 3. Thank you.